Good afternoon. This is Boaz Arberg. We will discuss this afternoon robot kinematics. We look at the physical environment, kinematic diagram, coordinate definition, variable definition, problem definition, and a general solution to the problem. Here's an example of a cylindrical robot. You see it has a revolute joint at the bottom. It has a prismatic joint going up and down, and a prismatic joint going in and out, and it has a gripper at the end. We have a kinematic presentation of the robot. We call it kinematic diagram. We call this robot RPP, revolute joint, prismatic joint, and prismatic joint. And basically we like to show on a kinematic diagram the direction, the positive direction of the degrees of freedom. I also like to show some reference to a scale so we could tell what type of size the robot that we analyze in is going to be. The next phase is to assign coordinate system to the various degrees of freedom. And we have 3 degrees of freedom to define the position of the tool center point in space. We assign the inertial coordinate system to the bottom of the robot. Then the next coordinate system, which rotates about the inertial frame with the revolute joint, is x1, y1. Then the second joint is going to be located at some point along the z1 axis, and we define that coordinate system as x2, y2, and z2. To assign variables, we like to assign position, velocity, acceleration to all the degrees of freedom so we can use them in the analysis. Over here, the revolute joint has a position theta, angular velocity omega, angular acceleration alpha. We have the position in coordinate system 1 of the second joint, which we define as r1. Its rate of change in time is v1, and the second derivative or acceleration is a1. And we also have a position of the tool center point in coordinate system 2. We define that as r2, and we also define the velocity and acceleration in this coordinate system as v2 and a2. To look at the definition of a problem, we're looking for the velocity of the tool center point in the inertial coordinate system. This is the absolute velocity. We define it as dr dt. We're also looking for the absolute acceleration of the tool center point in the inertial coordinate system, and we like to see the components of the absolute acceleration of the TCP in coordinate system x0, y0, z0. What's given to us is the joint motion of the robot, including theta, omega, alpha, r1, v1, a1, r2, v2, a2. So given all of that, we're looking for the velocity and acceleration and components in absolute coordinate system. The general solution, we start by looking at the position of tool center point in the inertial frame. We define that r equals to r1 plus r2. You see r1 plus r2. The absolute velocity of the tool center point will then be the absolute velocity of r1 plus absolute velocity of r2. You see that in this equation, the absolute velocity of r1 is given to us as the relative velocity of r1 in its own coordinate system 1, plus omega, which is the relative angular velocity of coordinate system 1 with respect to coordinate system 0 cross r1. But r1 is pointing in the z1 direction, and omega is also pointing in z1 direction. Therefore, the cross product of two vectors which point in the same direction is 0, so this term will cancel. And then we have the absolute velocity of the tool center point in coordinate system 2 is its relative velocity, which we defined as v2 plus omega cos the vector itself. So there will be in the direction from omega rotated in the direction of R2 will progress right hand screw in direction of y2. So the velocity, the tangential velocity, will be in this direction of y2, and this is called the radial velocity, v2, along the radius. The absolute acceleration of the tool center point will be similarly the relative acceleration of A1 in coordinate system 1. It has no effect of the rotation because it's along the same line, plus the absolute, the relative acceleration of R2 in coordinate system 2, which is A2, plus the tangential acceleration alpha cos R2 will be a tangential acceleration in direction of y2, plus omega cos R2, which is the centrifugal acceleration pointing towards the center of rotation, plus the Coriolis acceleration, which will be 2 omega cos v2. And again, we can find that out if v is in this direction and omega is in this direction, then the Coriolis will be again in direction of y2. Then finally we have the direction of the gravitational acceleration in the minus z2. It will be a magnitude with 9.8 meter per second square, and the magnitude is going to be a unit vector. The direction is going to be a unit vector in a minus z2. To resolve the absolute acceleration as we'll find it here into coordinate system 0, what we have to do is we have to actually first find the resolution of this vector, which is the absolute acceleration in coordinate system 1. To do that, we take the resolution in coordinate system 2 of the acceleration and we transform it to coordinate system 1 by this matrix of transformation 2 to 1. And then when we have the vector resolved in coordinate system 1, we can further transform it to coordinate system 0 by heating it with the rotational matrix which transform it from 1 to 0. So the net result will be a matrix which is transforming a vector from coordinate system 2 to coordinate system 0. Now, if we look at the transformation of coordinate system 2 to 1, it's a unit vector because there's no rotation between 2 and 1. And therefore, there's only translation in the z direction. Therefore, that's 1 in the diagonal and zeros every other place. However, the rotational matrix from coordinate system 1 to 0, as we found in previous presentation, is cosine on the diagonal 1 along the axis of rotation, which is the z. This is the position, zeros on the columns and the rows, cosines on the diagonal, and then sine off the diagonal with a minus sign that we have to check its direction as we discussed in previous presentation to find out where the minus is in this position or in this position. So this concludes our presentation of kinematics related to this particular one is a cylindrical robot, and we'll take a look in upcoming presentations on the graphical solution for this problem and also on the analytical solution for this problem. Thank you.